Hello everyone and welcome to Magnetic Circuits course video number 5, Losses in Magnetic Circuits and Magnetic Coupling. Let's start. In this video we are going to cover AC sinusoidal excitation, size of magnetic devices, losses in magnetic circuits, hysteresis and eddy current loss, mutual inductance, and we are going to wrap up this course by a summary. For the magnetic circuit shown in the figure, what happens when we apply a sinusoidal input? This is what we call it AC sinusoidal excitation. And the answer is, the flux will be a sinusoidal function as well, something like that one. 5t equals phi maximum cosine omega t. But we know from Faraday's law that the induced voltage across this coil will be E of t equals minus d lambda by dt, which equals minus n d phi by dt, where lambda equals n phi. We covered that one in the previous video. So let's differentiate the flux now. So E of t equals n phi maximum omega sine omega t, and omega equals 2 by f, where fs is a supply voltage frequency in hertz, or s stands for the source. So the relation between the voltage and the flux will be as shown in the figure. So what is the RMS value? So let's take the peak divided by root 2. So the E RMS value will be 2 pi over root 2 n phi maximum fs, which equals a well-known equation that's 4.44 phi maximum fsn. Let's take an example. An iron-cored inductor shown in the figure is to be designed to give a required inductance L of 2 Henry. The magnetic circuit of the inductor has a mean iron path of length 200 mm and area 10 to the power 3 mm square, made from a material with relative permeability 4000 and an air gap of length 1 mm. So we need to calculate the total reluctance, the number of turns required to give this inductance, the current through the inductor when the coil is excited from a 50 Hz 500 volt voltage source and the coil resistance is negligible, and the peak core flux density in this case. If the resistance of the coil is 500 ohm, what will be the flux density? So let's start the solution now. So given that L equals 2 Henry, L equals 200 millimeter, area is given 1000 millimeter square, and we have mu R equals 4000 and G, the air gap, is 1 millimeter. What will be the equivalent circuit? The equivalent circuit that we have Ni, which is something like a battery here, R iron and R gap. So, the total reluctance of the magnetic circuit is R iron plus R gap. So, R iron equals L over mu node mu R area. That one equals 39.79 10 to the power 3 ampere turn per Weber. Regarding the gap, G over mu node area, mu R for the gap is 1. And please note that the area is 1000 millimeter square. So, you need to multiply by 10 to the power minus 6. So, that one for the gap equals 795.8 10 to the power 3 ampere turn per Weber. The total reluctance will be the addition, they are in series, so that one equals 835.6 10 to the power 3 ampere turn per Weber. Once we know the total reluctance, we can calculate the number of turns N, because the inductance equation L equals N square over reluctance, so N equals root LR, so that one equals 1293 turns. We know the total number of turns now, so that one is going to give us inductance of 2 Henry. What will be the current? So to calculate the current, we need to know the reactance. Since the supply voltage is sinusoidal and coil resistance is neglected, the current through the inductor can be calculated by determining the coil reactance. X equals omega L. So the current I equals V over X, V RMS 500 over X equals 2 by FL. So in this case, we have a current 0.79 ampere. So now we can calculate the peak flux density. We calculated N, the number of turns, we calculated the current. So we can use the MMF equation where Ni equals phi reluctance and phi equals B multiplied by A, which is the area, so we can calculate B. But bear in mind, in this equation, you need to adjust it to have the peak value by multiplying by root 2. So B equals root 2 Ni over A reluctance. And you are going to have the value here 1.73 Tesla. N is calculated from the previous slide, the current is calculated before, and the reluctance is calculated as well. Can we calculate the flux density from another equation? Yes, we can use the AC sinusoidal excitation, where VRMS equals 4.44 phi maximum Fn, and phi maximum equals B maximum area. So, B maximum equals VRMS over 4.44 area multiplied by Fn. So 500 over 4.44, 1010 to the power minus 6, 50 Hz, 1293 turns. That one is going to give you the same value for the peak flux calculated from the MMF equation, 1.73 Tesla. What is the flux density if the coil has a finite resistance of 500 ohm? In this case, we are not going to deal with reactance, we are going to deal with impedance. So Z equals root R square plus X square, root 500 square plus 628.32 square. That one is going to give us the magnitude of the impedance, 802.98 ohms. So the current will be V over Z, 500 over the impedance Z. That one is going to be 0.62 ampere. Remember, it was before 0.79. Now it becomes 0.62. So what is the new flux density in this case? We're going to use the same equation as we used before for the MMF equation, root 2 Ni over A reluctance. So root 2 multiplied by 1293. The change here that the current is not 0.79, the current is 0.62. So the flux drops, the peak flux drops to 1.36 Tesla. Can we use the AC sinusoidal excitation equation? In this case, you need to calculate the voltage across the reactance only. So, if we want to use the AC excitation equation, we need to calculate the RMS voltage across the inductor. And then we can use the formula. So, how we are going to calculate it? Voltage across the reactor will be the current multiplied by the inductance. So, the voltage now will be 389.56 volt. So, the 500 volt will be applied to the RL. What is the voltage across the coil alone or the inductance alone? That one will be 389.56. So from this one we can calculate the B using the equation 4.44. So B maximum equals VRMS over 4.44 area Fn using the voltage only across the coil. So that one will be 389.56 over 4.44, 1010 to the power minus 6 multiplied by 50, 1293, give you the same answer we calculated from the MMF equation, which is 1.36 Tesla. So let me repeat that one again. If we like to use the AC sinusoidal excitation equation, we need to calculate only the voltage across the reactance. Size of magnetic devices. The AC sinusoidal equation E equals 4.44 phi maximum Fsn, where phi maximum equals B maximum area, is going to guide the size of the something like inductors, transformers, ferrite cores. So, the maximum flux density is limited by the material. For example, B maximum is in the range of 1 to 2 Tesla for iron or in the range of 0.3 Tesla for ferrite cores. So, for a certain voltage E, RMS value, we have the choice of balancing it from the equation Fsn area. So, three factors here: frequency, number of turners, and the area of the core. So from this equation, if we like to increase the voltage, let's increase the number of turners. Increasing number of turners requires more turners on the coil, which increases the overall device size. So let's increase the area. So increasing the cross-section area requires a larger cross-section area of the magnetic core, which increases the overall device size. So let's increase the frequency. Increasing the frequency reduces the number of turners and the cross-section area, therefore reduces the overall device size, which is fantastic. So let's increase the frequency without limit. Can we do that one? So from the previous slide, we looked for increasing the frequency to increase the voltage, but from the size perspective, an increase in frequency appears very beneficial for reducing the core size and cross-section area. However, losses in magnetic material can limit the usable frequency range. These losses are usually lumped together called iron losses. So this is a problem. So this equation we need to optimize between the cross-section area and the number of turns and the frequency. Increasing the frequency without limit is going to increase the iron losses. Iron losses will be divided to two categories: eddy current loss and hysteresis loss. So we are going to look for them one by one. To understand the hysteresis loss, we need first to understand what is the hysteresis loop. Assume we have a magnetic circuit or a magnetic core. We are going to apply AC current with frequency F to this core. So the flux initially starts from a point like A here, and once the current increases for first time, so the flux is going to have a path which is AB. When the current starts to fall down, so the flux is going to follow another path which is BCDE. If the current is going to increase again, so the flux is going to follow another path which is EFB. And because the current has a frequency F, so this loop is repeated, which is BCDEFB. So the amount of flux in the core depends on the applied current and the flux previous history. The dependence on the preceding flux history and the failure to retrace the flux path, we call it hysteresis. So the outer path, which is BCDEFB, is called the hysteresis loop. We need to define some major points in this hysteresis loop. For example, point C, residual flux. When we apply the MMF for first time, so the flux is going to follow the path AB. When the currents start to fall down, so the flux is going to follow the path BC. The point C is not zero. When the force is removed, the flux in the core does not go to zero. This magnetic field is called residual flux or residual magnetism. Another point, point D. So that one is called corrosive MMF. To force the flux to go to zero, an amount of MMF, known as corrosive force, is applied to the core in the opposite direction. And that one is going to force the flux to reach zero. What is hysteresis loss? So it is the energy required to reorient domains. So the area enclosed by the hysteresis loop, formed by applying the AC current to the core, is directly proportional to the energy lost in the given cycle. So we can say that the hysteresis loss is proportional to the flux density and the applied frequency. But the question, how we can prove that this loop represents energy loss or something in what? Let us see. To answer this question, we are going to use a simple mathematical proof where we are going to make a line integral for this closed path. So we are going to calculate the area enclosed by this path. So the x-axis will be the H, which is field intensity ampere per meter, and the y-axis is the flux density Weber per meter square. So closed line integral HdB equals HB. H is in the units of ampere per meter and B Weber per meter square. So that one equals ampere Weber per meter cube. From Faraday's law, E equals d lambda by dt. Lambda has the units Weber, E the units volt, and T is second. So Weber equals volt second. So we are going to substitute here. And that one is going to give us ampere volt second per meter cube, which is joule per meter cube. Joule per unit volume. So that one is energy per unit volume per one cycle. If we multiply joule by the frequency, so joule multiplied by cycle per second, that one is going to give you power per unit volume, watt per meter cube. If we multiply by the volume, so this loop represents power lost in watt. Second type, eddy current loss. If we have a time-varying field passing through a metal or piece of iron, Faraday's law will be applied here. That one is going to induce small loops of electric current as we can see in this figure. These loops are called eddy currents, but these eddy currents waste energy by generating heat within the metal. This energy loss is called eddy current loss. So P loss equals I square R. So from that one we can conclude that P loss is proportional to the square of the frequency and 1 over the resistance. How we are going to reduce these eddy currents? What we are going to do, either reduce the frequency or increase the resistance. Sometimes we cannot reduce the frequency. So the solution is to increase the resistance. How we are going to increase the resistance? Using laminations. So when the core is split into thin insulated layers, we call it laminations, each layer acts like a barrier. The insulation between layers increases resistance, making it much harder for large eddy currents to flow. In conclusion, laminations limit the size of current loops and increase resistance. A device like transformer or any electrical machine should be laminated because they are subjected to time-varying field. So for example, if we're going to use the transformer at 50 Hz, we can use laminations within the range of 0.5 millimeter. If we're going to increase the frequency for something like 100 to 500 Hz, we can use 0.35 millimeter. For 500 and higher will be 0.2 millimeter. For something like 1 kilohertz, 0.1 millimeter. If we are going to use high frequency operations, we can use ferrite cores. Before going to explain the mutual inductance, I'm going to introduce the circuit's convention. If I have two coils like those, this means coils with air as the coupling mechanism. If we have the symbol like this one, so this means coils with iron laminated as the coupling mechanism. If we have these two bars or two lines in the middle will be dashed, so coils with ferrite core. So time now to start the mutual inductance. Mutual inductance. To understand the mutual inductance, we need to remind ourselves about the self-inductance. So changing the current in a coil produces a time-varying magnetic flux. This flux links to the same coil, inducing an electromotive force according to Faraday's law, where E of t equals n divided by dt. I'm going to ignore the negative sign now. I can rewrite this equation as E of t equals n divided by di by dt, which is L di by dt, where L equals n divided by di. If we integrate, so in this case, L equals n phi over I, where n phi equals lambda. So lambda equals Li. Lambda the flux linkage, L is the self-inductance, I is the current. What will be the case if we have two coils in the same magnetic circuit? If two coils are placed on a common magnetic circuit as shown in the figure. So the magnetic flux produced by one coil will link the other, and vice versa. This interaction gives rise to what we call it mutual inductance. Still, we didn't understand what do you mean. We are going to look for that one from the perspective of each coil, one by one. So let us assume that coil number 1 is excited while coil number 2 is open circuit. What do you mean by that one? So coil number 1 has number of turns N1 and there is a current I1 of t is injected to this coil, while coil number 2 has a current 0. So coil number 2 has number of turns N2. What we can see here that there is a flux phi 21. This flux is going out from the coil number 1 is going to link the coil number 2. And there is a leakage of flux which is in a yellow color. So we have two colors here, red color and yellow color. Yellow color is the leakage flux, while the red one is the flux is going to link coil number 1 and coil number 2. So in this case, we have a voltage induced in coil number 2. So if coil number 1, which has a number of turns N1, is excited while the other remains open or inactive, so the changing current in coil number 1 produces self-inductance in the same coil and mutual inductance to the other. So how we are going to put those in equations? So E1 of t equals N1 d phi 11 by dt. So what's phi 11? So we have leakage plus flux linkage. So the flux for the coil number 1, we call it phi 11, which is phi leakage number 1 plus phi 21. Why we call it phi 21? Because that one is the flux is going to link with number of turns N2 due to the current I1. So E1 of t equals L11 di1 by dt. So that one is the self-inductance for this coil. So L11 equals L leakage 1 plus L21. So L leakage 1 is straightforward. That one is the leakage for this coil. But L21 is N2 d phi 21 by di1. So the number of turns N2 due to the current I1. So we have two inductances here. So the self-inductance of this coil in total will be L11 equals N1 d phi 11 by di1. So the flux due to the current I1. And if we like to calculate the mutual or the induced voltage in the second coil, so induced voltage in the second coil will be N2 d phi 21 by dt, and the inductance produced by the mutual will be L21 equals N2, which is the number of turns of the second coil due to the current in the first coil. So this time we are going to have coil number 2 is excited while coil number 1 is inactive. So this means that the current of the coil number 1 equals 0 while we have a current I2 of t. So we have a flux which is a blue color. That one is a linkage of flux from coil number 2 is going to link coil number 1, and we have a leakage of flux which is a yellow color here. So if coil number 2, which has a number of turns N2, is excited while the other one remains open, so in this case the changing current in coil number 2 produces a self-inductance, and at the same time that one is going to produce a mutual inductance with coil number 1. We are going to put that one in equations as well. So the induced voltage in the coil number 2 now equals N2, depends on the number of turns of the second coil N2, d phi 22 by dt. What's phi 22? Leakage plus linkage. So that one is phi leakage 2 plus phi 12. So why we call it phi 12? So that one due to the current in the coil number 2 and going to link coil number 1. So in this case we have L22, which is a self-inductance of this coil. So L22 di2 by dt. But what about the mutual? So L22 equals L leakage 2 plus L12, and L22 equals N2 d phi 22 by di2, and the voltage induced in the coil number 1 will be N1 d phi 12 by dt, which equals L12 by di2 by dt. What's L12? N1 N1, the number of turns of the coil number 1 due to the current I2. So L12 equals N1 d phi 12 by the I2. If coils number 1 and 2 are energized simultaneously, as shown in the figure here, so we have coil number 1 has a current I1 of T and coil number 2 has a current I2 of T. So we have a self and a mutual for each coil. So the total flux linkages become a combination of self and mutual components. So the total flux on coil number 1, we are going to call it phi1, and that one is the sum of the flux due to the self and mutual. And the same for coil number 2. So phi1 equals phi11 plus or minus phi12. Why plus or minus? That one, it depends on the direction of the current in the second coil. So if the flux is going to help or to oppose the flux from coil number 1. So you can find that the blue color is going to support the red color or opposite to the red color. If the blue color here, like what this one, so if that one is going to help phi21, so that one will be, if it's opposite, that one will be negative. So in this case, or in this figure, phi21 and phi12 are opposite, so we can take it negative. But I put the equation in general, so phi11 plus or minus phi12. And for phi2, the flux, total flux in the coil number 2 will be the self of the coil number 2 plus the mutual, plus or minus, it depends. So that one is phi22 plus or minus I21. So L11, the self-inductance of coil number 1 will be N1 d phi11 by the I1. So that one will be the self-inductance for the number of turns N1, coil number 1, due to the current I1, while L12 will be the number of turns N1 due to the current I2. This is why we call it phi12. And for the second coil, L22, the self-inductance of coil number 2 will be N2 d phi22 by the I2, will be the number of turns for the second coil due to the current I2. What about the mutual? L21. So that one will be N2 d phi21 by the I1, will be the number of turns of the second coil due to the current. Let us summarize the mutual inductance now. I remove the magnetic circuit and I put the two coils now. So we have all the fluxes, flux for coil number 1, flux coil number 2. So phi11 equals phi21 plus phi leakage 1. And phi22 equals phi12 plus phi leakage 2. So the self-inductance of coil number 1 is L11 equals N1, the number of turns of the coil number 1, phi11 over I1. That one due to the current I1. And for the coil number 2, the self-inductance of coil number 2 is L22 equals N2 phi22 over I2. What about the mutual? The inductance of coil number 2 due to current I1 will be L21 equals N2 phi21 over I1. And the inductance of coil number 1 due to current I2 will be L12 equals N1 phi12 over I2. So the total flux of coil number 1, we call it phi1 equals phi11 plus or minus. That one, it depends on the direction of the current I2, phi12. And phi2 equals phi22 plus or minus phi2. So now, if the system is linear, so we can say that L12 equals L21, we are going to call it M. And we know that the lambda flux linkage equals Li, so we can write now the equation lambda 1 equals N1 bracket phi11 plus or minus phi12, or we can write it as L11 I1 plus or minus Mi2. That one if the system is linear. And lambda 2 equals N2 phi22 plus or minus phi21. That one equals L22 I2 plus or minus Mi1. And for any electrical machine, you should start from these two equations. So M is the mutual inductance. So that one equals K root L11 L22. So K is called the coefficient of coupling, and K is smaller than or equal 1. The maximum coupling when K equals 1. For no crosstalk, so that one is 0. For ideal transformer, for example, K equals 1. For the practical transformer, will be in the range 0.95 to 0.99. Circuit conventions or dot conventions. We noticed in the previous slides that you plot the magnetic circuit while I1 of t and I2 of t, there is a small black dot beside them. What that means, this is what we call it dot conventions. So for example, the equation lambda 1 equals L11 I1 plus or minus Mi2. How do we know that the mutual is positive or negative? We are going to use this convention, dot convention. So we have positive mutual if the current flows into the dot in each circuit. Look here, so the current is in, so that one is positive mutual. The current is in, positive mutual. So we have negative mutual if the current flows into the dot in one coil and out of the dot in the other. So that one is in, that one is out, so that one is negative mutual. That one is in, that one is out, that one is negative mutual. That one is applied for two coils are connected in series, for example. Let's take another example here. We have coil number 1, coil number 2, so that one has L1, that one has L2. The dot is here and the dot is here, so that one is I, so that one is positive mutual because the current is in for both dots. If we have a coil like this one, and that one will be the second coil, L1, L2, the dot is here and the dot is here, so the current is in and the current is out, so that one is negative mutual. Now we can summarize this course. So in this course we cover the following topics: sources of magnetic fields, the magnetic circuit structure analysis with the analogy of electric circuits are introduced, the relation between field density and the field intensity with emphasis on the magnetization curve, BH curve, and we identify the permeability, how to calculate and design the self-inductance, Faraday's law and AC sinusoidal excitation, size of magnetic devices and magnetic losses, eddy current plus hysteresis, mutual inductance, and circuits convention. See you in the next course.